All right, ready? Need another minute? I see lots of movement, so I'll wait one more minute. All right, we ready? Let's do it. So we take a sample proportion, and I say calculations. I just hate to interrupt calculations.
This way?
I know. I haven't done it in my head. Is that what Daniel got? If it is, I would say it's. Okay.
What do you think?
All right.
See, I thought that's true.
Point 4, 8. Yeah, that's good. Looks like you did all the steps the right way.
Yeah.
I think so. All right, let's do it. So we get a sample proportion of 65%. That's just an estimate, though. We want to give our boss, our board of directors, an interval, plus or minus some number of standard errors of this 65%. So how do we calculate the standard error?
0.65
0.65.
times 1 minus 0.65.
Yeah. Divided by 100.
Square root that.
Square root that. What do we get? What do we get for this?
0.48.
0.048. Do we like that? So about 5%. All right, if we want to be 90% confident, what is our z-value going to be?
1.65
Excellent. So,
times 0.48.
our confidence, yep, exactly. So our confidence interval is going to be 0.65 plus or minus 1.65 times 0.048. All right, what do we get for our lower bound? 571, I like it. 57.1%. What do we get for our upper bound?
I got 0.73.
73%. Do we like those? Yeah, pretty wide confidence interval. Why is the confidence interval so wide? Sample size of 100. Okay, so the sample size were larger, and this would be smaller. In any case, how do we interpret that? It starts with I am 90% confident.
True population, proportion
Yes.
is, between, 57.1% and 73%.
Yeah? Excellent. Excellent. Any questions on any of that?
Did you do this?
You get that? That was right, Kyle?
I thought, yeah.
That's what you got. Fantastic. Oh wait, no, don't close this. I want to minimize or whatever. All right. All right, so let's try to get a few pieces of this next section under our belt before we take a break. Is that good? Unless you want to take a break now. No answer? All right. So, all right, are we ready? All right, so let's move on to estimating difference between two population means. We're going back to a mean. So this is not a proportion, this is a mean. Mean income in the town is 72,000. Median income in a different town is 61,000. So that's a difference of 11,000. That's just an estimate. All right, how do we calculate the confidence interval for the difference in town A versus town B? We're gonna do something. What's that?
You start squaring.
Square. Oh, is that what you did in the last one? That's what happened?
That's what you're doing.
Oh yeah, we're gonna square stuff. So we're gonna look at the sampling distribution of the sample mean difference. Should sound familiar, right? Predictable sampling distribution properties. Also sounds familiar, right? Building the confidence interval. Sounds completely new, right? No. All the exact same thing. All right, so let me go through a thought process here. So I've got two towns. I've got town A and I've got town B. Actually, you know what? Before I even go through this thought process, let me bring up a couple points. So we're doing mean differences. So the difference between town A and town B. Now you already have a tool to calculate this, right? You already know how to calculate the average income in town A with a confidence interval and the average income in town B with a confidence interval. So town A, town B, the skills you already have, you might say 95% confident that the average income is between 68,000 K and 72 K. All right. Town B, 95% confident that the interval is 79 and 84 K. Okay, so you remember, you already know how to do that, right? Right? So if you were to estimate the mean difference, there are some ways you could do it. You could say, well, maybe I'm going to take the bottom one here and the top one here. Or maybe I'm just going to take the middle point. Or maybe, I don't know, I'm going to do some combination of the bottom one and the top one. I don't know exactly how I should do it. Also, there might be a completely different standard deviation here as compared to this town. So it might be mixing apples and oranges if we try to combine these two. But the point I want to make is you already have a tool to give you an idea of how you would estimate the mean difference. So mean difference meaning difference of this mean from this mean. That's what we mean when we say mean difference, and you already know a little bit about how to do that. What statisticians have done for us is they've given us some formulas to combine these two things, to be a little bit more precise in the way we calculate it. So with that, I'm going to go through the same thought process we've gone through in similar discussions. Suppose I were trying to find the mean difference in town A and town B, so I take a sample in town A, I take a sample in town B, I take the difference, and now I have a mean difference from one sample. And it comes out to be $13,574. That's my difference in population A versus population B. I'm going to do that one time, I'm going to put it on a frequency distribution. Then I'm going to do it again
For 10,000.
for 10,000 times. Next time it comes out to be 9,000 something. Next time it comes out to be whatever. I do this 10,000 times, over and over again, put all of them on a frequency distribution. What will the shape of that frequency distribution be?
A bell curve.
Bell curve. It will follow all the same properties. Except this time we're going to call it sampling distribution of the sample mean difference. N's. Okay. Sampling distribution of the sample mean difference is the probability distribution of all possible values of the sample mean difference. X bar 1 minus X bar 2. All right, remember X bar 1, this is, X bar is sample mean. So this is sample mean 1 and sample mean 2. When sample size N1, that's sample size from population 1, and sample N2 is taken from another. Okay, now, let this, what is this little symbol? Mu1 equal the mean of population and mu2 equal the mean of population 2. So just remember, X bar is sample mean, mu is population mean. Okay, the difference between the two population means, so this is the true difference between the population mean. Mu1 minus mu2. And then our point estimate of the difference between two population means is X bar 1 minus X bar 2. And we're going to calculate X bar 1 minus X bar 2 with our sampling. And we're going to do it 10,000 times, and we're going to put it on a frequency distribution. And we are going to create the sampling distribution and the sample mean difference. Right, properties. Number 1, it will be normal for sufficiently large sample sizes. Sufficiently large means that both samples are 30 or more. Remember last week we liked 30 or more as a sufficiently large sample size. Only difference here is we need both samples to be 30 or more. It is centered around the population mean difference. So what is this? Mu1 minus mu2? What is this? Population mean difference. What's the population mean difference?
Difference between the entire mean of the population 1 and the population 2.
Exactly. So in reality, these are just estimates. But in reality, population mean 1 is 74,279. Population 2 is 71,600 and whatever. It is truly, in reality, the real number. Population 1, population 2, the difference. All right, when we do our sampling distribution and sample mean difference, the most common outcome is going to be the true mean difference for both populations. Why wouldn't it be? We would be accurate, would be the most likely outcome, the true difference, as long as our sampling techniques are good. Now, this sampling distribution, the sample mean, has a standard deviation. And how do we combine standard deviations from population 1 and population 2? Well, the answer is we do it this way. The standard deviation, this X bar 1 minus X bar 2 means standard deviation of the sampling distribution of the sample mean difference. All right, we're going to factor in the population standard deviation of town 1, square it, population standard deviation of town 2, square it, divide both those by the respective sample size, square root the whole thing, and that's going to give us our standard deviation of the sampling distribution of the sample mean difference. And there we have it. So, sampling distribution of the sample mean difference. All right, now what is this little, the mean of this distribution is what? Tell me what those symbols mean and why that's the mean of this sampling distribution.
What's the average of the population 1 minus the average of the population 2?
Yeah, and that can be summarized with the term,
Mean difference.
yes, so this is the true population mean difference, is going to be the center point of this sampling distribution of sample mean difference. And what is this little thing right here?
That is sample mean.
Yeah, sample mean difference, and what that means is, for the notation here, that means we're putting, each time we sample, we take the sample mean 1 minus sample mean 2 and we graph it here. That's just a graph of 10,000 of these. All right, and then what does this whole term mean? Somebody tell me, just notate this little part of the term. How do we describe that? That is the
Standard deviation of the sample mean difference.
hello, yeah, I could go with that. I would prefer standard deviation of the sampling distribution of the sample mean difference. I would prefer standard deviation of sampling distribution of the sample mean difference. I could go with standard deviation of mean difference. What I could also be okay with, what's the shorthand version for this?
Standard error.
Standard error. And it is calculated this way. All right, so let me do the notation here. So I want standard deviation. I'm going to do standard deviation of this, the sampling distribution and the sample mean difference. Now why do I put x bar 1 minus x bar 2? Why don't I put mu 1 minus mu 2?
It's a sample.
Because there's samples. This is a frequency distribution of all those samples. All right, and it's going to be that. All right, it's going to be calculated that way. All right, and then I want the mean of this. X bar 1 minus x bar 2. Again, I say the mean of x bar 1 minus x bar 2 because this is a sampling distribution of sample means. It's not true population mean. And that is going to be equal to mu 1 minus mu 2. Yeah. Okay. Any questions? All right, how about confidence intervals? Well, remember this, x bar 1 minus x bar 2 is our point estimate for the mean difference. All right, town 1 versus town 2, difference of 5,000, plus or minus, z, based on our confidence interval. And then this part right here, what's this again? Standard error. All right, this is how many standard errors we need to go plus or minus. Because our z-score tells us that, but this is the standard error calculation. All right. Estimating the difference between means of two populations, large sample sizes, population standard deviations are unknown. Now remember, what's the general rule when the population standard deviations are unknown?
Standard, sample.
Yeah, take the sample standard deviation and do one other thing.
Minus
Do we use z usually?
T.
We use t. That's what you did for your homework for this class, and that's what you did for one of the quiz questions. You used t. Normally that's the rule, and you will continue to do that for just one mean. However, when you're doing mean differences, statisticians are okay with using z. The reason they're okay with using z is because there's so many different components. They say there's so many different moving parts. Chances are it's just going to average out to an accurate representation. Maybe the sample standard deviation here is going to be off by a little bit, but the standard deviation here is going to be off by a little bit in the other direction possibly. There's so many moving parts that they figure it's all going to add up to a normally distributed sampling distribution and sample mean, so you can just use Z. Does that make sense? All right, so we take our sample mean difference plus or minus our Z value times number of whatever we calculate our standard error to be. Let's do an example. Page 290, exercise 8.6.
Can you wait for a second?
What's that? Yeah, oh, wait,
Or you can get it. You do 53, 5.3 squared divided by 50, like that.
oh, this is the one we're about to do?
Yeah,
That looks right.
yeah, no, that, on the calculator, would I just do one at a time, or do all at a time?
You could do them all in one. You would have to put parentheses and be very careful with the way you do it on your calculator.
Yeah.
All right, what had happened here? So we're looking at 290 exercise 8.6. All right, here we go. Oh God, I hate this one. Just because the wording is so complicated. But nonetheless, we will persevere through it. Operating microwave transmitters at high temperatures can drastically reduce their reliability as measured by number of errors. All right, so we're looking for number of errors per 100 megabits of transmitted data. All right, that's all. That's all I was scared about. Now we know we're looking for number of errors per 100 megabits of transmitted data. Temp Labs is testing two different transmitter designs, design A and design B, in order to estimate the difference in average high temperature error rates of the two designs. Suppose Temp tests a sample of 50 designs for A and transmitters and 50 designs for B transmitters under high temperature conditions and discovers that the average error rate of 22.3 for design A and an average error rate of 17.6 for design B. All right, 90% confidence interval for error rates in the two population. Assume standard deviations are, we know sample standard deviation for 1 is 5.3, sample standard deviation for 2 is 4.6. Okay, so we've got two designs and we test 50 transmitters, design A, 50 transmitters, design B, just based on the raw numbers, the mean for each one. Which one do we like better? Do we want error rates to be high or low?
Low.
Yeah. So which one do we like better?
4.6.
Yeah. So we're liking transmitter B better. All right. We think that's better just based on our estimates. And in fact, we think the point estimate is what? 17 point difference between these two. 22.3.
4.7.
Yeah, so 22.3 minus 17.6 equals what, Kyle? 4.7?
Yes.
All right, so design A has 4.7 more errors per 100 megabits. So we like design B. But we cannot confidently say that we're sure the difference is 4.7 errors per 100 megabits. Why can we not confidently say that yet? This is just a sample. And we need a confidence interval. It's just a point estimate for a sample. So we're going to take this 4.7 plus or minus some number of z's times our standard error. Alright, let's work on the Z part first. 90%. Okay, so what do we need for our Z value at 90% confident? 1.65. 1.65 times, alright, we need a standard error, also known as standard deviation of sampling distribution of the sample mean difference. Alright, and we've got to calculate that this way. 3.5 is sample standard deviation population 1. 4.6, sample standard deviation population 2. Square both those, divide those by 50, add them together, take the square root, and it comes out to 7. What does that come out to? Anyone know what this comes out to? I guess they don't give it to us directly. They don't. Yeah, they don't.
1.8, I got 1.18, I didn't know.
One.
Assuming I did right.
1.18. I'm.
So I did it separately, I did 5.3 squared divided by 50, and I got 0.75. And then I did 4.6 squared divided by 50, and I got 0.65.
Okay, so I think what Kyle is going into is you need to find a way on your calculator that works for you and just be very careful with the way you plug it in. If that works, great. In terms of the actual answer, I'm not really liking 1.18. It's close, because I know,
0.985?
yeah, I like that one,
That's before the square
0.985.
root, though.
Oh, you forgot to square root it, maybe?
No, I square rooted it.
You did before the square root.
Yeah, that's before the square root.
Okay, alright, so.
0.99.
Okay, I like that one,
How did you do it
0.99.
in your calculator? You did it all under the same square root?
No, I did it 5.3 squared over 50, and then 4.6 squared over 50, added those, and then the square root.
Then you square rooted at the bottom?
We use square root, wait, so it's the square root of 0.985, which is the 5.3 squared over 50 plus 4.6 squared. You separate it out. Otherwise you're getting too involved in, I mean for me, you're getting too involved in too many parentheses, and if you miss one.
Yeah, it's just something you need to get fluent with. Get used to your calculator. If Excel works for
5.3
you,
squared.
then you
So
could
5.3
go that
times
route.
right.
So if you crunch all these numbers, the square root, this part, just including under the square root and the square root, you'll get 0.99. And then you'll multiply 1.65 times 0.99, and you'll get 1.64.
So before you square, you get 498,
Before you take the square root, yeah.
you get 498.
Alright, so then our confidence interval is going to be our 4.7, our point estimate, plus or minus 1.65 times 0.99, which is going to equal 4.7 plus or minus our margin of error, 1.64. And that's going to give us, what do we get for the lower bound? 3.06?
Why is it 1.64 instead of 6.5?
It's 1.65 times 0.99.
Oh, okay, I get
It
it.
just so happens to be a confusingly
Okay.
similar answer. And the lower bound is 3.06, upper bound is 6.34. So, can someone interpret that interval for us? It starts with I am 90% confident. Or not, yeah, go ahead, I'm 90% confident.
True population mean differences between 3.06 and 6.34.
Good, excellent. Laura, why don't you give it a try?
I am 90% confident that the true mean difference is between 3.06%, no, 30.6% and 63.4%.
Yeah, they're actually not percents, those are numbers.
Okay.
Yeah, so 3.06 and 6.34 errors per 100 megabits. I guess they could, yeah. Yeah, it's deceiving because they're out of 100, but they're technically not proportions. All right, is this making sense? All right, well, let's go on to the next. Do you wanna break now, or you wanna do the next one and then break? Break. All right, let's break. Let's take. Let's come back at 8:12, and then we'll start the next example.
I have a question for you.
Yeah.
The one question was an extra credit. If you didn't get it right, you didn't. Why do I get
Yeah.
4.5 out
What's-
of 5? Because you get the 2 questions right, and then the third was like
Oh.
credit.
Did you use? Okay. All right. So you missed. Is your question about the extra credit?
Yeah, if you don't get it right, why do you don't get a 5 out of 5?
Oh, because you got. I happen to remember that you lost 0.5 on the second question because you used the z distribution instead of the t distribution.
Okay. Is there any way you could show me for that, or?
Yes.
Can I
Pull
get
up your
the exact
blackboard.
answer?
Yeah, pull up your blackboard. This is actually going to be fun because I know
Funny for you and not funny for me.
it's fine.
I'm messing.
You still got it. It doesn't matter. It's going to be funny because using the wrong distribution is so close. But I just happen to know you used the wrong distribution because you got the exact wrong answer.